Hello, everyone. Welcome to the new event, the ESO Hypatia Colloquium. Thank you for being with us today, and congratulations. As you know, this is an ESO series of seminars dedicated to early career scientists. And we are all the time, I always remind that and underline the fact that we are very, very happy and impressed by happy to host this event, and very, very impressed by the outstanding quality of our speakers. I remind you that early careers means that the speakers are either already still in the PhD phase or just a few years after the PhD, up to 3 years. So considering this, the quality is really, really remarkable. That we are very, very proud and happy to see this. At the end of this series, we will publish the book of proceedings. That this is the one of last year that you can find the PDF online on our Hypatia pages, and there will be a new one this year. With all the contribution from the speaker of 2022. I just very, very quickly, please be reminded that you can participate into the event and make questions, ask questions or make comments to the speaker, either by the chat on Zoom or by raising your hand if you are on Zoom, or if you are watching the event on YouTube, you can use the live chat to send the comments to the speakers, considering that there is always a 20 seconds delay between the time the event is happening live and broadcasting on YouTube. Please be aware that this event is broadcasted and will stay recorded in a playing list on the YouTube channel of the Hypatia. So if you're uncomfortable with that, please leave you should please leave the event and join the event directly on YouTube. You can also send comment anonymously by using a form that is available on our pages, where you can also find the entire program of the series. And then the thing is that if you go to the program, you see the title of the talks, and you click on the title, you do not only see the picture of the person, you can see the title, you can see the abstract, but also a full CV that you can download. With that, I would like to thank Sabrina and Alonso today. Sabrina is a master student at ESO. Congratulations, so super enthusiastic young upcoming researcher, basically, and Alonso, who is a PhD student, who is doing a PhD at ESO. So we are very happy to host them. They will be the chair of the session. So thank you very much. And with this, I would like to give the word, in fact, to Sabrina, who is going to introduce the first speaker. Thank you very much. And Sabrina, yes. Hi, Sabrina.
Hi, everyone, and thanks, Giacomo. I'm happy to present you the first speaker of today, Sebastiano von Fellenberg. He finished his PhD last year at the Max Planck Institute for Extraterrestrial Physics and is now a postdoc at the Max Planck Institute for Radio Astronomy. And today he will tell us something about young stars in the Galactic Center. So please, Sebastiano, if you're ready to share your screen, the floor is yours. I will stop the sharing here now.
Thank you, Sabrina. Let me quickly switch. And do you see my slideshow now?
It's loading at the moment. So I see the slide. Yeah, thanks.
Perfect. Thank you. Thank you for inviting me, first of all. And I'd like to start off with a topic in the young stars in the Galactic Center. The young stars in the Galactic Center is actually a quite old research topic, and has been studied since the early 90s and even a bit before that. The Galactic Center young stars were first discovered as a peculiar set of sources, point sources around Sagittarius star. And what people saw is that, well, if you look at the helium line here in this map from Krabit 91, you can see that there's these sources which have very broad emission lines. That's of course peculiar, and in the beginning it wasn't quite realized what these sources were. And with this paper, it was understood that in fact what we are looking at is a set of sources that is so-called Wolf-Rayet type stars. Wolf-Rayet type stars are incredibly big stars, incredibly heavy stars, which have gigantic outflows. And I think of them as being essentially constantly blowing up. And in these in gigantic outflows, you have these very broad emission lines. And in back then, it was very puzzling to find these stars there, because them being so heavy means that they have a very short lifetime. And that means that they must have formed very recently. Back then, it wasn't clear if there was indeed a massive black hole in the galactic center. But this was actually very puzzling, because it was very confusing to find these very young stars there, because traditional pathways of star formation doesn't involve a massive black hole to next, which completely dominates the dynamics of any gas cloud in the region. Of course, it then became clear that there is indeed a massive black hole in the galactic center, and one then has to answer the question of how these stars could have formed in the galactic center. There's three main scenarios that have been discussed in the literature. The first one is the so-called rejuvenation of young stars. So in the galactic center, there's a huge amount of old stars, and there's so many old stars that it's actually possible that these old stars could in principle collide and just look like young stars. So two old stars make a big heavy star, and then maybe these were just rejuvenated old stars that look like young stars. A second scenario is the so-called in-spiral of a cluster. So there the idea was maybe these young stars didn't actually form in the galactic center itself, but with dynamical friction on the old star nuclear star cluster would lose angular momentum and then move towards the black hole. And then what was thought of in the beginning as impossible, it was found out if we have just enough gas in a massive enough stellar disk, people then were able to show that you can in principle have star formation in a gaseous disk. Now, two of these scenarios have been more or less disfavored by now. And the first rejuvenation scenario has been disfavored by studying the spectra of these young stars in more detail. And specifically, what was detrimental in this effect was Symphony and Osiris integral field observations of the galactic center, which are just observations of the galactic center where every pixel you get a spectrum. And with that, you can disentangle the stellar light from the background, which is also a lot of emission lines. And you were able to show that these spectral lines of these young stars, so here you see not a Wolf-Rayet type star, but an O type star, was really looking like a classical, perfectly normal young star that formed about 6 million years ago. So this rejuvenation scenario was with this method disfavored. The in-spiral scenario is also now by most people regarded as disfavored, because with more and more time, and I'm showing you here a study from Feldmayer-Krause in 2015, people showed that there is no trail of young stars that is falling towards the galactic center, and the young stars are centrally concentrated. And that is speaking against this idea where you have a young star cluster basically migrating towards the galactic center. And this leaves us with the local formation scenario. In a local formation scenario, what you need is this gaseous disk. And indeed, if you study the dynamics of these stars, you can see if you, for instance, look at the radial velocities here, and if you here plot the radial velocity on the y-axis against the declination position of the star, you see this clear preference. Or here in the study from Levin and Belodorov in 2003, you see the same thing in the projected velocities. So this showed that the young stars, at least a fraction of the young stars, live in a stellar disk, consistent with being formed in a gaseous disk, of course. Now, the study of these young stars continued, and the number of known young stars ever increased. So what you see here is a plot from Lu, I think 2009, where they show the angular momentum distribution. So what you see here is a sphere, essentially, of the sky, but what is plotted is in the x direction, the big omega of the so the longitude and latitude essentially of the direction of the angular momentum, and you see this clumping of angular momentum in this one direction. And what you can see here is just what you saw before in this x and y position, a structure that we now know as the so-called clockwise disk. The study of these young stars then continued, and in 2009, Bartko et al. Introduced the idea where when they studied the angular momentum of the young stars with function of distance from the black hole, they showed that if you go here away from Sagittarius A star, so darker points are stars, or the preferred angular momentum direction of the stars away from Sagittarius A star, you could see that the angular momentum changes. So the idea that was presented in Bartko is that you have a centrally located structure, the clockwise disk, and this clockwise disk then changes as you go away from the galactic center, forming this warped disk of young stars. However, this idea of the warped disk was then challenged in a later paper, which included even more stars, and there they showed that if they use a bigger sample and if they assume or compare the sample, that only the angular momentum direction of the clockwise disk seems to be significant, while other features here do exist. They argued that these other features must be more similar to an isotropic distribution, where stars that have been scattered off that clockwise disk just end up and locally concentrate, but they've favored a non-warped scenarios, but just a central disk together with an isotropic cluster or more isotropic cluster of young stars. And this is essentially the situation where my study then picked up from. So this is just the same type of study that has been done basically for 20 years now, just with an ever bigger sample. And if you see here now, we have around 200 young stars in this direction, and our coverage of spectroscopic observation forms pretty much a square patch forming around 30 by 30 arc seconds in the galactic center. Now, what can we do with observations like these? And I'm now going to try to explain how these orbital angular momentum plots are actually made. And the idea is that, well, the first thing that we get from a young star, once we've identified it, is the position in X and Y. If we have a set of photometric observation that is just long enough, what we'll see is the star will start to drift. These stars are far away from the black hole, so the drift is actually not that large, and it will just resemble a linear motion. If you're closer to a Sagittarius star, you then of course get these beautiful orbits with, of course, the star S2 or SO2 forming the 16-year orbit around Sagittarius star. Now, now we have 4 space phase coordinates, so the X and Y position and the projected velocities in X and Y. And if we have spectroscopic observations, this allows us first to identify the stars as young or just boring old stars, if you want. And it also gives us a radial velocity if we see the star, how the line is shifted with respect to the rest frame velocity. What we can never get in these observations is the Z position. So if the stars are far away and we don't see an acceleration in the trajectory of the stars, we don't know the depth of the star. But what we can still do, we can assume something about the Z distribution. And we can write down a prior on the Z values. And here I was using a so-called isotropic cluster prior. So the assumption is that, well, let's assume all young stars are sort of in a relaxed distribution. And then with the observed values in the other phase space coordinates, we can write down a prior function and sample from that prior function. We can then also sample from the observed X, Y, Vx, Vy, Vz values. And with that, we can calculate orbital elements distributions. 2 of these orbital elements, the I and the big omega, give you the direction of angular momentum. So this is how we get the plot that I showed you from before. If you have a singular star, you will sort of get a blob here, which gives us the angular momentum direction. If you have many stars facing in the same way, what we'll get is essentially an overdensity of angular momentum in one direction. And this sort of looks like the clockwise disk, right? If you have another disk in the galactic center, for instance, or the angular momentum direction changes as a function of distance from the black hole, what you get is essentially just another blob here. If you were to bin up your data in this sense, you would then be able to differentiate between the two distributions, and you can look for, by binning the data, you can look for these overdensities. And this is exactly what we did in the study. So we started off with the first radial bin slice. So here we're starting at 1 arcsecond. So we're not concentrating on the innermost stars. We're starting a bit further out at 1 arcsecond. And we've just refined the good old clockwise disk, which extends further. So even if we go up to 4 arcsecond, we see. But what we also see is sort of the fuzzing out of this clockwise disk. And then in the intermediate bin, what we see is this sort of warping of the disk again. And in our study, this warping of the disk is actually significant if we can detect it, if we compare it to an isotropic distribution. However, the significance of this warping of the feature is quite low, statistically speaking. So there's really just a couple of young stars that seem to change, seem to belong to this clockwise disk and then changing its angular momentum direction. If you look on the opposite side here, you see a sort of new feature popping up. And this is on the lower part of the sphere, and that means that it's rotating on the other way, in the opposite sense. So this is a counterclockwise feature here. And it gets really interesting once we are in this range where our data is essentially the most new or compared to other studies, and where we've added the most young stars. And what you can see here is that there is essentially 3 very bright features. 3 very bright features. And essentially we have a counterclockwise feature here, which is something that has been discussed as the counterclockwise disk in the literature quite a long time already. And then we have these 2 features here and here. This feature was also sort of known in the past in Bartco. There were hints that this would sort of be an extension of this clockwise warp disk. However, this feature here is new. So this is really a new sort of dynamical component in the young star distribution. And then in the last bin, we essentially see it's just the remnant of this outer features here. Now we want to learn more about these features, and the way I did this is by looking at by essentially turning around our question and say, let's look at in which direction the angular momentum looks. So let's write down a prior for the angular momentum direction. Here I'm going to show you 2 angular momentum direction, one pointing toward the clockwise disk and one sort of pointing to the warped part of the clockwise disk. And now then let's look at the data and let's calculate how likely it is for each star in our data to belong to this feature. With that, we get an evidence and we can do an evidence cut, and we just get the most likely members belonging to one of these directions. And here's how that looks like. So in this plot, there's a couple of things. First of all, you see these radial bins here. They have absolutely no meaning in this. They're just there for orientation. They just give you the idea of what was of the binning before. And you see stars that are green or blue. And of course, these are the stars that are very likely belonging to this or this feature. What you can also see is sort of the direction of the stars. And what you can see is that, well, the clockwise disk stars are forming a sort of clockwise feature that you look on. And if you look at the pluses here, this gives you the angular the radial velocity. So this is really just a sort of more or less face-on rotating disk. And then indeed, if you look at the slightly changed angular momentum direction, you can see that, well, all of these stars out here, and even though it's, I think, only I forgot, I think it's 11 young stars that belong to this outer feature, they really fall out far. You can also see all the other young stars which belong to neither of these features, and you can see, oh, there's quite a lot of them. However, what we've not used in this is any information on where the stars are. So the fact that these stars go out and see this sort of warping distribution, this is really not imposed in the data in any sense, always saying what is the angular momentum direction, and then we naturally get out this sort of warping feature of this clockwise disk. Now, if we go to the outermost bins, I was talking about these 3 features here, and here are the members of these 3 features. You can see here, this is the counterclockwise feature, which just looks like the the clockwise disk, but rotating in the opposite sense. What you need to notice here is, of course, the much bigger scale. So this goes up to, so what I was showing before is this inner part, and here is essentially this outer part. And then we have these two features, which are sort of two edge-on looking features. One is this F2, and the other one is this F3, which are here. The next thing that we can do is look at the luminosity function, so the K-band luminosity function of these stars, which is really just a histogram of the number of stars per square per area, and their brightness. So here are more bright stars, here are fainter stars. Of course, here we also have to take into account a completeness correction, because all of our data is different integration depth, different integration time, and you need to account for that. But what you see here is a sort of a rising function, and if you compare this with other forks, this is essentially consistent with more or less a power law increase, and this should be consistent with sort of a standard Salpeter-Cupra type of initial mass function that you derive from the K-band luminosity function. However, if you look at this other dynamical component of the clockwise disk, here is where all these very bright Wolf-Rayet type stars live. So what we see is essentially that this clockwise disk here, and here I'm combining both this inner and outer feature of the clockwise disk, it seems to be very top heavy with a lot of very bright stars, but very few fainter stars. And then if you compare this with the other features here, you see that, well, the bulk of young stars actually is at a larger separation. So they sort of form this more consistent with a normal type of K-band luminosity type of population. Now, now I want to go into various different types of interpretation of this data, or how did the young stars form? And here I'm just going to pick out one of the many ideas, which is from a simulation by Hobbs and Nayakshin. And I apologize to everyone who's also worked on this. And as you can imagine, there's a lot of people that have had great ideas on the matter. But here's one which I found quite a remarkable resemblance with our observations. So in this simulation, the idea is that you take two massive gas cloud and you collide them outside of the galactic center. Due to that collision, they lose angular momentum and they start to fall onto the black hole. So they accrete towards the black hole. And with this accretion process, you start to form a central region in which you have a central accretion disk, but you also have these outer streamers or filaments here. The central disk then circularizes, so the eccentricity changes. And while on the outer shroud, the outer parts of the ring, the eccentricity stays higher. And if you compare this with our observations, this is quite a remarkable resemblance here, right? So here you have this more central feature, which could correspond to this innermost region, and you have these outer features, which would correspond to these sort of outer filaments. And what is important in the simulation that after sometimes, I think here about 60 million years or 60,000 years, stars start to form in both these outer filaments as well as in the clockwise disk. I just brushed over this, but when we look at the eccentricity distribution that we get from our calculations here, it seems to favor that these outer features tend to be more eccentric compared to these inner features. So then this seems to be consistent with the predictions from the simulation. And lastly, this study also looked at the star formation or the masses of the stars that form in the different feature. And the statement here is that, well, if you're closer to the black hole, you need much more mass in order for stars to clump. So they'd expect a different initial mass function or a K-band luminosity function for stars in this inner region and this outer region, which is of course also what we've seen in our data. And lastly, this simulation was only going up to 60,000 years. And because of course, after that, there's a lot of things going to happen. What the galactic center is a pretty complex system where you have a black hole, of course, but you also have this nuclear their star cluster. And here I'm telling you that there's 5 more sort of dynamical massive components in the galactic center. And then outside you also have massive gas clouds, and there's a lot of mass. And what this means is that there's a lot of different dynamical timescales which all sort of act and worked on the orbital elements of an individual stars. And what this means is that if you look at this plot here from Kosic and Tremaine, that at the distance of the clockwise disk, there is several timescales that are relevant. And most importantly, there's these so-called vector resonant relaxations that sort of change and work on the inclination and the big omega, so this the angular momentum. That means that stars can efficiently change their direction of angular momentum in the expected lifetime of this observation. And I think in this study, this was only considered the black hole and the nuclear star cluster. So of course, if you even have a more complex system, the story is going to be even more distant. So what I'm saying is that maybe even if we didn't form such a complex structure in the beginning, there's plenty of processes which can change and alter our observed gaseous disk from which the star is formed into the observed distribution that we see today. And with that, I would like to thank you and point you to the paper, which is on AstroPH since last Tuesday, so exactly a week ago. It's accepted in FCUL letters, and will hopefully come out and be done with proving in very soon.
Thanks, Sebastiano, for this great talk. I already see applauding hands. So yeah, you made a really good job. And with this, let's open the floor for questions, either via Zoom or as well during the YouTube chat. I will have a look if I already have some here. Yeah, Giacomo, please go ahead.
Yes, Sebastiano, congratulations, and their spectacular work and data set, certainly. I was wondering, do you, I don't know if it makes sense, this question, so sorry but do you see, is there any way to see, first of all, when you say young star, how do you classify young star? So what is a young star exactly for you?
So in our so in the galactic center, how this works is essentially that we look for stars that are brighter than essentially 15th magnitude or something, and then if you see bracket gamma lines, we know that these stars must be young, right? Just from how they are.
Emission lines,
yes,
basically.
Yes.
Okay. And do you, because it would be interesting, do you expect or do you see small age differences between the stars?
Well, in our study, we couldn't do that because what we're looking for is essentially a backup observation. So our spectra tend to be not as nice as the ones that I showed in the beginning, but so we can't do that. However, there's detailed studies of young stars of bright young stars and the young stars very close to the black hole. Mm-hmm. And there is actually very little evidence that these stars have different ages. So they all seem to be formed 6 million years ago. But of course, there's many attempts to disprove that. And in our study, it's of course perfectly reasonable to also assume that there's different ages, because well, we see a different K-band luminosity function. So if we assume that the stars are of different age, and since most stars are fainter outside, further outside, they can also be older in principle. So if we had multiple star formation epochs, this was also perfectly fine. And there's of course papers and ideas that discuss that, and I cannot. Unfortunately, I cannot say which of it is. It's perfect. Both is perfectly consistent with our observations.
Yeah, because there is a spectacular combination of dynamical, interaction, of course, an impact of dynamics on the way stars are forming and when, how, why. This is all there. It's a beautiful laboratory, really. Sorry. Thank you very much.
You're welcome.
Thanks. These were exactly the two questions I had as well to you. So I can directly hand over to Alonso, please, with the next question.
Thank you, Sabrina, and thank you, Sebastiano. Wonderful talk. I was wondering also a little bit about this luminosity function, how your results impact that, and what we can learn about these luminosity functions. I think it's your slide number 9.
I'm sorry, I don't quite get what you want to ask.
Yeah. So depending on what curve you see, you have different.
So I mean,
I understand correctly.
In everywhere else than in the galactic center, my understanding is that star formation seems to have the same sort of initial mass function, and if you look at stars that are not old enough, you will be quite close to this initial mass function. So the idea here is that past studies have studied that is that you take this K-band luminosity function, and from that you can then model how the masses were distributed in the young stars. And there's this sort of universal power laws of star formation, and the only case where I know of is that in these clockwise disk stars seem to be more top heavy. This has already been discussed in previous studies, so this is not a new result in my work, but so here the idea is that maybe because it's such an extreme case of star formation, you end up with a different sort of initial mass function of the stars. Is that what you wanted to ask?
Yeah, exactly.
Yes. Okay.
Exactly, thanks.
Okay, Julia, please.
Yeah, hi Sebastiano, nice.
Hello, Julia.
I have a question that is actually similar to Giacomo's and basically a bit of a follow-up on that one. So if I get it correctly, then you have similar ages for all of the stars, at least for the ones that you know of. So my question is, why? What happened 6 million years ago? Why was there suddenly star formation in the galactic center? And are there indications that there's going to be another phase of star formation soon, or yeah, why did that happen?
So it's a very broad question, and there's of course many different ideas of what happened and how stuff happened. What we do know is that there was this star formation event, at least one star formation event 6 million years ago, right? Potentially more star formation event in time, but at least there must have been one 6 million years ago. We also think now that there's this one, or that this happened in sort of a gaseous disk that accreted onto Sagittarius A star. What is very intriguing, and what I always find very interesting, is that if you look at X-ray observations of the Milky Way, you see these big blobs around it, right? And you also have these Rosita results that show these in the X-ray. And if I understand correctly, and of course I'm not an X-ray astronomer, but these tend to be also seem to have ages hinting towards 6 million years ago. So what this, to me at least, looks like there was a big star formation event 6 million years ago that maybe even turned into AGN activity. Of course, the realm of possibility is very large. And yeah, does that answer your question? Or
yeah, it does. Thanks.
This was quite a very interesting question. Let me have a short look at the YouTube chat. I can't see there any questions. Are there any other open questions from the Zoom? If not, then I would thank you again, Sebastiano, and would hand over to Alonso, who's presenting you the second speaker.
Thank you very much, Sebastiano, again. Thank you, Sabrina and Giacomo. My name is Alonso Luna. I'm a PhD student here at ESO Hypatia, and today is my pleasure to introduce you to Víctor Almendros-Abad, who is a last year PhD student at the Universidade de Lisboa, Portugal, and also visiting ESO Hypatia. Today he will talk about brown dwarf formations. So, Víctor, the floor is yours.
No, I didn't mute myself. Okay. Are you seeing my screen?
Yes.
Okay.
Good.
Perfect. So, okay, hello everyone. First, I would like to thank the organizers for giving me the opportunity to talk at this very fine program. And today I'm going to be talking about the work that I have been doing during my PhD so far, which you can see here in the title, where we are studying the brown dwarf formation and whether there's an environment dependency. And in particular, I will be talking about the results, the latest results that we got on these very beautiful clusters shown here in the picture. This is the work that I've been carrying out with these people here and more. So this is just an outline of what I've I'm going to be talking about today. So I will be talking about how do these objects form, how can we maybe estimate the role of the environment on their formation, and then I will go on to determine how can we determine the initial mass function, do also some stops on how can we estimate the youth of objects using their spectra. And then lastly, I will present our results that we get on this cluster in GC2244. So brown dwarfs are basically astronomical objects that are not massive enough to sustain hydrogen fusion in their centers, meaning that they are supported by electron degeneracy pressure. And their main characteristic is seen here at this plot here, where you see the luminosity time evolution of objects with different masses. And if you look at these later ages, you can see that stars, they reach this main sequence where they maintain their luminosity, whereas you have brown dwarfs below here, below this hydrogen burning limit, where below where you have brown dwarfs that do not burn hydrogen, and then you have their evolution with time, where you can see that they keep evolving with lowering their luminosity and also their spectroscopic properties. And one of the main unanswered questions about these objects is, well, how can these objects form? Well, we know more or less how do they form, but well, there are a lot of unanswered questions here. So it has been shown that they can form like stars from like a turbulent fragmentation of the molecular cloud. It has also been proposed that they can also form like planets, so they form from this fragmentation in the protoplanetary disk, and they get ejected by some dynamical process. But you could also imagine that you can have a star in the making or a high mass brown dwarf in the making that by some dynamical process or some process they get their either ejected from their mass reservoir, or they get their accretion halted or something like that, and then they get kind of like a failed star that is a brown dwarf. And a proposed formation mechanism for brown dwarfs is also the ejection of embryos from multiple systems that you can understand here. They get ejected from this mass reservoir. And also if you have an object close to a massive star, the winds of these obvious stars will also truncate the disk of these objects. But what we know of brown dwarfs is that they, in general, share many properties with stars, or at least they have a smooth transition between stars and brown dwarfs that do not hint any big difference in the properties of these objects. And the current consensus is that the majority of brown dwarfs, at least in the higher mass regime, they form like stars. But there's always the question of what happens at lower masses, where we have very few censuses, and we know very little of these objects. And also, what is the relative importance of these other proposed mechanisms that in principle should also work for the formation of brown dwarfs? So how can we be able to discern between these different formation scenarios? And the main question that we are trying to answer is whether the environment affects brown dwarf formation. This is a very hot topic in general in astronomy, because this is also being looked at in the higher mass regime with the salpeter slope. But here I'm just going to be focusing on what would be the effect on brown dwarfs. Because we know that it is expected that high gas and stellar densities should increase the brown dwarf formation efficiency. In particular, for these three mechanisms, for the three of them, it is expected that if they are the dominant formation channels, then brown dwarfs should form more efficiently. And you obviously also have this, you have in a cluster a higher amount of obvious stars. If these obvious stars are indeed an efficient way of forming brown dwarfs, then you would also expect an increase in brown dwarf formation. And here, so how do we normally look for these environmental differences? Is through the initial mass function, which is the distribution of masses at birth in the beginning, but it is the distribution of masses at the age of the cluster that you are looking at. And here I'm showing a set of a lot of initial mass functions from Young clusters, open clusters, globular clusters, also from the field. This is from several years ago. But the main point that I want to stress here is that the IMF is generally it can be parameterized by two power laws, one at the higher mass, which could be, which has this general value of the salpeter slope, of close to salpeter slope. And then we have these lower masses that can also be parameterized by a power law, with this exponent alpha, which is typically found in nearby star forming regions to be between 0.6 and 1. So in general, we find a universality of this value. But the problem is that nearby star-forming regions have low densities in general, and they have few to no novice stars, meaning that we are not tracing very different environments. So it's actually, in the end, very difficult to say, even if there were any differences in the IMFs, what would be the actual reason of this difference. And that's why we started this new program called Young Brown Dwarfs, where we have selected a few massive young clusters where to study the brown dwarf population. And these clusters are shown here, and here I highlight, sorry, I highlight the properties of these three clusters in terms of their environment, so in terms of their stellar density and the originating of stars. Were selected so that these properties were different, so that we can constrain this formation mechanism. And in particular, I'm going to be talking about this cluster here in the center. In particular, we have been studying it so far in the very core region of the cluster, so the very few inner parsecs. So, okay, we have this cluster, we have NGC 2244, and we want to actually obtain their IMF, so we have to obtain their cluster members. So here I'm showing the CMD of the cluster, well, towards the cluster. So you have J versus J minus K, and I also saw the 2 megayear isochron, which is the estimated age of the clusters, and this isochron is shifted to the distance of the clusters, which is 1.5 kiloparsecs. And at higher masses, which is what I'm showing here, above 0.1, 0.2 solar masses, we have kinematics, we have colors from several surveys. And in a paper that we have very recently submitted, we have studied the white region of the cluster using kinematics from Gaia and colors from several surveys, which after applying a machine learning method called probabilistic random forest, we obtained the members of this wider region of the cluster. And here in the bottom two panels, you can see the locus of the training set that we used in terms of the scalar magnitude diagram and the proper motions diagram. And we also had some optical spectroscopy from BIMOS at the Very Large Telescope, which we reduced and analyzed. And here at the right panel, I'm showing the final members that we get as orange circles. But what you see here is that the members that we are able to get from all these available surveys don't only get down to 0.2, maybe 0.1 solar masses. So this means that we are not able to get into the brown dwarf regime that we are interested in. So in this regime below 0.1 solar masses, we only have photometry from this work that was led by Cora Music in 2019, where they studied the core region of the cluster using only photometry. But here in this talk today, where I'm going to be presenting is our results using spectroscopy. Because if you obtain a spectroscopy of all of these, they are not even member candidates because they are just objects in this catalog, in this brightness range. If you obtain the spectroscopy of one object, you can confirm both the low mass and yellow nature of these objects. And with that, you can obtain a keen sample of members. The main drawback and the reason why this is very difficult to do is because it's very expensive, because you have to obtain an individual spectra of each object, or you can use also some multi-object facility. And in this first part of the talk today, we'll be talking about the efforts that I have been carrying out with the first part of my PhD towards trying to develop a homogeneous spectroscopic analysis, especially focusing on the youth analysis. And in order to do that, we compiled a dataset of all available near-infrared spectra of low mass stars and brown dwarfs. So these were almost 3,000 spectra in the near-infrared, because this is where these objects peaked in brightness, so JHK bands between 1.1 and 2.3 microns. And we selected the spectral types between M0 and L3, which is from low mass stars to brown dwarfs, and from L3 there are almost no very young brown dwarfs known. And we divided this dataset in 8 classes because we want to see because the main point of this work is to try to see the difference in 8 classes and try to look for new tools and ways to perform this classification. And the first thing that we did here is to homogenize the set of spectroscopic parameters of the entire dataset, which means the spectral type and extinction. And we did it by comparison with spectral templates. And once we had that, we went further in the evaluation of different spectral type tools, and we use in this case the spectral type indices, which we found 6 different indices that worked pretty well. And if you use them in the combined manner, even if you use them individually, they provide a reliable spectral type measurement. In fact, 2 of these indices have been newly defined in this work. But the main part of this work, which is what I want to be talk about more is the youth evaluation, the looking for some youth signatures actually in this spectrum, because they can be low mass, but they have to show some youth signature in order to be confirmed as a member of a young cluster. And here I'm showing 6 different spectral indices. You see in the y-axis the spectral index, in the x-axis the spectral type that we obtained, and they are separated in colors by the age class that we defined. But you can see here that these first 5 spectral indices from the literature kind of separate these classes, especially the Young-Hanfield classes, from M6 more or less. We have this last spectral index that we defined in this work that seems to work better than the others. Maybe I'm biased because we defined it here. But if we look farther into this index here, we are looking at in gray we have the same spectral index, and in gray we have the field objects, and the rest of the objects are color-coded by their age. And you see even a gradient in age in the spectral index, which is very interesting. And we performed some further evaluation of these youth analysis using machine learning methods. And here I'm just going to show one case scenario that we evaluated, evaluating for only 2 young classes, so for Young-Hanfield classes. And I'm only going to show the results of these 2 methods, for which the input was the entire spectrum dataset. So the input was the entire spectrum dataset that was previously homogenized. And the first method was, for the first method, we performed feature extraction using principal component analysis, and we performed classification using support vector machine. And the second method, we applied directly random forest to the entire dataset. And what you can see here in the top 2 panels, the confusion matrices, I'm seeing here showing the precision recall metrics, and both of them are over 98%. So this means that we can perform an almost perfect separation between Young-Hanfield objects. And here in the bottom panels, you see the spectral index diagram, that the TLIJ index versus spectral type, and you see how the age class probability is here, and you see that how can we perform even better than using only a spectral index. And a very interesting result here is that from the random forest, we can also extract how important is each feature that we input for the youth evaluation. And in this case, as the input was the entire spectrum, what we see is how important is each region in the wavelength range for the classification. And here we can already identify a lot of known features that have been used for age studies. Here in the J-band alkaline lines, in the K-band the sodium doublet, that the main feature that is used for that is identified that the most important feature is the broadband shape of the H-band, which is a very well-known feature, but with this we saw that it is actually very important for the classification. And in fact, this very big peak here that we find is also the location of one of the bands by which the spectral index that we defined is located. So this kind of links the 2 ways that we have tried to perform this age evaluation, which is very interesting. But if we go to a cluster, you can imagine that I've been talking about the spectroscopy because we actually obtained a spectroscopy of this cluster. So we did that using CMOS in the Very Large Telescope. This is a multi-object spectrograph which has 24 arms. We use the HK filter, which performs from 1.5 to 2.3 microns, with a mean spectral resolving power of 1500. And we obtain spectra for 85 objects that you can see here in the color magnitude diagram, that they are below the locus of where Kaya can go. And here is a sample of 4 objects that were confirmed as members. You see what is how do they look like, and we performed the analysis of these objects. First, we had to perform kind of the low mass analysis, so the derivation of spectral type of an extinction of those objects that actually showed the low mass shape. And for all of these low mass member candidates, we performed the youth evaluation. So the main argument that we use for their youth is, as I just said before, is these spectral indices. So here I'm showing the 3 spectral indices that fall in the wavelength range of CMOS, of our CMOS observations. The 2 indices and the right panels, I have already introduced them, especially this second one, which is the one that we find. And this third index is one that we also observed to work very well. You can see our objects here lying over the different objects of our dataset. And we also use for further confirmation of their youth, we compare them with Young-Hanfield spectral templates to see whether any of these sets performed a better fit. And we also use the age that we got from the HR diagram to further confirm that they are actually young. And with this, we obtained 30 new members of the cluster, new low mass members below generally 0.1 solar masses, which include the first bona fide brown dwarfs beyond 1 kiloparsec, at least to our knowledge. You can see them in black circles. I highlight that black circles here in the color connected diagram. And we had to study further this low mass range of the cluster because the census is not complete. Because you see here in the subnet version of the CMD, we didn't observe all the objects in the catalog, so we are missing some brown dwarfs. In order to complete the catalog, we divided the CMD in grid cells, and we obtained the contamination rate of this KMOS sample in each grid cell, and we applied this grid cell, the grid cell contamination rate to the rest of the objects in the catalog. And this is the same. We follow the same methodology from our previous paper from the using only photometry. And with this, we can now combine all the members. We can obtain the effective temperatures. We obtain the masses and age from the HR diagram, which you can see here at the right plot, the HR diagram for all the members that we got. And we can get the initial mass function, which is the main result that we wanted to get here. So here I'm showing in the x-axis the mass in solar units, solar mass units, and the y-axis represents the number of objects per mass beam. And you see how we here parameterize the IMF by a broken power law at more or less 0.3, 0.4 solar masses. And you see that the higher mass slope is more or less, well, it's around 2.1, which is kind of in agreement with saltpeter, but we don't want to get into that. But at this lower mass regime, we see within this value of 1.2 with kind of high errors of 0.1, that if we compare with nearby star-forming regions, this value is kind of steeper than what we found in star-forming regions. But we can also see that maybe, so this value of J equal 19 is down the brightness that which we extrapolated the membership of the KMOS sample, which should be approximated to more or less 30 Jupiter masses, but it seems that we are not completely down to this magnitude rather than 45 Jupiter masses, and that's why we think that this is the best fit that we can make to the IMF low mass slope. And if we compare, so this here, I'm showing the IMF of this other cluster from the massive young cluster from our JOBT program, which has high stellar density and richness in nova stars. These two different studies we have performed on using only photometry. The top one represents studying only the core region of the cluster, and the other one the wider region. And you see that the low mass IMF can be represented by a power law with a slope 0.6, 0.7, which is pretty much in agreement with nearby star-forming regions. And if we compare with a previous result of the same cluster, same region, using only photometry, this value was approximately 1, which kind of, I mean, in the end is also in agreement with error. So we cannot argue here that we are seeing a very different behavior than nearby star-forming regions, because this result is in 3 sigma in agreement with nearby star-forming regions. But we can also study the population of brown dwarfs in the clusters through the star-to-brown dwarf ratio. This is the number of stars over the number of brown dwarfs in the cluster. It is typically defined between 1 and 0.03 solar masses down to 30 Jupiter masses. But as I said, I was discussing before, it seems that our completeness is not down to 30 Jupiter masses as we expected, but rather more or less 45. And here I'm showing the comparison of this value against nearby star-forming regions. It's also RCW38, this other cluster of our program. And it's comparing this star-to-brown dwarf ratio with the stellar density, and the hatched polygons represent the clusters with high number of OB stars. This means that in the end, we are kind of representing these two environmental properties that can affect, that we think that can affect brown dwarf formation. And we see that all clusters are in agreement with errors. Even if our cluster is on this very lower, on this lower part, it's still in agreement. Although I would like to note again that it may be this value is actually a higher limits, because we are missing some brown dwarfs. But as this cluster is characterized by only this high number of obvious stars and its stellar density is very low, we can maybe look more into what could be the effect of OB stars on brown dwarf formation. So in order to do that, we obtain the distance of each of the members of the clusters that we got to the nearest OB star in the cluster. Here I'm representing it against mass. And you see here that it seems that these lower mass brown dwarfs seem to be kind of closer to OB star. This is a very, very slight indication, because within errors, everything is in agreement. But if we look at the disposition of all these clusters, of all these members in the sky, so here I'm showing the OB stars as yellow circles, as yellow stars, sorry. Then we have the orange circles are the stars that are members of the clusters. Orange, blue circles are the higher mass brown dwarfs, and the diamond circles, blue diamonds, sorry, are the lower mass brown dwarfs below 45 Jupiter masses. You see that these lower mass brown dwarfs seem to kind of circle around this OB star here at the middle. This is actually very unexpected and very strange configuration, and also because this central OB star is the most massive here. So this is an O5 star, while the other three are B1, B2 type. But we cannot conclude from this that this is actually an effect of this central OB star, because in very loose regions such as Chameleon, which has no OB stars, we observe these objects that have been formed. So we cannot actually say much from this, but in any case, this is an unexpected configuration of these objects. Also, we would like to test these results on a wider region of the clusters, which is an ongoing work that we are doing. And with it, I'm going to leave you here with a summary of what I have been talking about. I thank you all for your attention, and I'm open to any question or comment that you may have.
Thank you very much, Victor. Very interesting topic and talk. And also thank you for sticking to the time. Well, in the meantime that people are raising their hands, I have a couple of questions. So you said that you and your team discovered and had the sample of the first brown dwarfs beyond 1 kiloparsec. So this is out of my field, but is this just because the depth of the instruments you use, or this has to do with your procedure and your data treatment? Well,
it's something that sounds very good. So it's something that it's always nice maybe to say, because it has not. So the main, so it's because of the instrument that we use, because we use the very large telescope, and we found them beyond 1 kiloparsec because previously I think that there was no one that had made strong efforts to try to look so deep in a young cluster. So that's why these are the first time that have been observed. But also this, the spectra of these objects are very low quality, and that's why it's very difficult to actually analyze them and actually confirm that they are young, which is a very important part.
Of course, I see. Thanks. And one other question, if you can answer it, if you can give us some spoilers or about these other two clusters that changes the environment.
Well, one of these other clusters, I saw it here. Yeah. Our results, it seems to be very much in agreement with the region. And the other cluster, I cannot say anything because we don't have results yet, but still ongoing the analysis of the photometric. So in this case, in these two cases, we only have photometry because it's impossible with the current instruments to go so deep using spectroscopy.
Oh, well, okay. Well, looking forward to it. And, okay, any more questions for Victor? Also not from YouTube. Well, thanks again, Victor, for the nice talk. And Sebastiano. Okay. Amelia says maybe moons will help Victor.
Definitely, yeah.
Well, get back to you, Giacomo.
Yes, thank you very much, Alonso and Sabrina. Thank you for sharing. And thank you to Victor and congratulations again to Victor and Sebastiano for the great talks and good all the best for the coming months and for your career. Looking forward to hopefully see you. Well, in your case, it's easier to see you physically, so you are more or less around. But it's always nice that we are going back to the normality that we were used to. So looking forward to see you around. And with that, I would like to thank also our people who attended the talks and for participations. Always very welcome. So we'll see you next week for another series, another talk for this series. Just to let me remind that there is end of May is the deadline, so it's a week still to the studentship program, the ESO studentship program. So if you are a PhD student, this is a program to support PhD students and who can spend from 6 months up to 2 years to work at ESO. So please have a look at the call and apply, consider to come and work with us. Looking forward to that. And with that, I would like also to remind everyone that we have an early career scientist visitor program at ESO now open. So this is a visitor program with which we would like to host PhD students up to 3 years, again, early career scientists to up to third year after the PhD, and to come to work with us for a minimum 1 month up to 4 months. Again, all the information are online, so please come and have a look at it. And if you have questions, don't hesitate to ask. And with that, really, I would like to close and thank you, everyone. And see you soon. Bye-bye. Ciao.